Hi everyone, Mr. Boltri here bringing you video 5.1. We're going to be talking about the first thing in Unit 5, rotational kinematics. So first we're going to do some circular motion terminology, and then we're going to talk about some rotational equations that you're going to need to know. So first, we've talked about this way back in Unit 1, but just as a refresher, for when something is moving in a circle, it is going to travel through some linear distance, and we call that linear distance the arc length. But also, if we think about the polar coordinates with a circle that has some radius r, it's going to be moving through some angle, which we call theta. And it's important that we measure theta in radians, not degrees, just in terms of to make the calculations work out in our calculator, which is weird because up until this point, we've been using degrees. But for the circular motion questions in the circular motion chapter, we're going to mostly want to keep things in radians. So you have probably seen the circumference of a circle as the circumference equals 2 pi r, or 2 times the pi times the diameter, 2 pi r. But the question is, what is the general equation for the arc length, the linear distance traveled, if we are going through any angle theta? So if we think about it, if we go through some angle theta, the linear distance traveled, the arc length is equal to r, the radius of the circle, times the angle theta. And you'll notice that the circumference formula is just a specific instance of the arc length formula, because if you go all the way around the circle, you've gone 2 pi radians. 2 pi r would give you the arc length for all the way around the circle, which we gave the name of circumference. So this is a useful formula to know in terms of just trying to figure out the linear distance based on the angle traveled and the radius. And again, just make sure your theta is in degrees, so you can actually get 2 pi, because it's not, the circumference equals 360 times the radius. That's not how we are going to be doing this chapter. So then the other two things that you're going to need to know is the angular velocity, which is not going to be the same as the linear velocity, and the angular acceleration. So angular velocity is going to be measured in radians per second. So if you go 2 pi radians per second, that means every second you're going all the way around the circle, which you can imagine if the circle is very small, 2 pi radians is not going to be a very large linear velocity. And if the circle is very big, then that is going to be very fast. But it's going to be the same angular velocity as long as you just go around in a circle once. So just as an example, we could imagine going around the inside of this clock versus the outside of this clock. If we went a whole 2 pi radians in 1 second, then around the inside, we wouldn't have to go very fast in terms of linear speed or tangential speed. On the outside, we would have to go very fast, but it would, again, be the same angular velocity. And then angular acceleration is just when the angular velocity is increasing or decreasing. So those are some terms that you need to know. So let's think about how do you figure out angular velocity and angular acceleration. So let's think back all the way to Unit 1. How do we figure out just linear velocity? Well, that was change in position over change in time to find the average, or the derivative of position with respect to time to find the instantaneous. So the same is going to be true for the rotational unit. To find the angular velocity, oh, by the way, I should say, the symbol for angular velocity looks like a funny W, but you are not allowed to call it W. This is an omega, and you must call it an omega, or maybe easier, you can just call it the angular velocity. But the symbol is omega, so don't ever call it W, either omega or angular velocity. So the angular velocity is the change in the angle, or the change in the theta, divided by the change in time, or the derivative of the theta, derivative of the angle, the angle through which you've been displaced, divided by, or with respect to time. So that's how you find the average or instantaneous angular velocity, or omega. And then likewise, if we think back to Unit 1 for how do we find the average acceleration or the instantaneous acceleration, it's the derivative of velocity with respect to time, or the change in velocity over change in time to find the average. And same thing, to find the angular acceleration, and the symbol for this, you'll notice, is a weird looking A. That's because it's an alpha. So you can call it alpha or angular acceleration. Or if I ever link one of Mr. P's videos, he calls it fishy thing because it looks like a little fishy thing. But alpha angular acceleration is the derivative of the angular velocity, omega, with respect to time, or change in the angular velocity over change in time to find the average. So the important thing to remember about the angular velocity and acceleration is it is basically exactly the same as the linear stuff, except instead of dividing the linear velocity, we're going to divide the angular velocity. So these should not be too mind-blowing or mind-boggling for you to just add to your tool belt of different tools. And so in a similar way, let's remember the big four equations of uniformly accelerated motion. So remember the big rule to use these four equations are the object must be experiencing a single constant acceleration. If the acceleration is changing, then you're going to have to use calculus and some other tools to solve the problems. But if we are lucky enough to have a single constant acceleration, then we are allowed to use these formulas. And it probably will be no surprise that to use the big four equations of uniform angular acceleration, we're going to have to meet the same criteria. We're going to have a uniform angular acceleration. And then we have a whole slew of tools that we can use to solve for a whole variety of different quantities. So you'll notice that these equations are exactly identical to the uniformly accelerated motion equations, except instead of linear velocity, we have angular velocity. Linear acceleration, we have angular acceleration, and change in position, we have change in the angular displacement. So I missed one right here. This should be a delta theta. But besides for that, we just change all of the x's to thetas, all of the v's to omegas, and all of the a's to alphas. And then we have our big four equations of a uniform angular acceleration. So this will allow us to solve quite a few problems as well. And then just to remember, when something is moving in a circle, we talked about this way back in Unit 1. But when something's moving in a circle, its velocity is tangent to the circle. Its instantaneous velocity is tangent to the circle, and it's experiencing some centripetal acceleration towards the center of the circle. The centripetal acceleration causes the object to change direction. Remember, acceleration is a change in velocity, which is sometimes a change in the magnitude of that velocity, a change in speed, and is sometimes a change in the direction of that velocity. The centripetal acceleration is causing the object to change the direction of its velocity. And then if the object is speeding up or slowing down, it's also going to have a tangential acceleration, which is going to make the velocity vector itself bigger, a change in speed, or smaller, speeding up or slowing down. So this is going to cause a change in direction, centripetal, and then tangential is going to cause it to speed up or slow down. So if the angular acceleration is 0, then the tangential acceleration is also going to be 0. But the centripetal acceleration will still need to be there, because if the centripetal acceleration is 0, then the object is not moving in a circle. It's going to move in a straight line. So it's going to be important for us to be able to know how to calculate these 1, 2, 3 quantities as well. And just the tricky thing is, don't mix up tangential velocity and the angular velocity, because tangential velocity is still meters per second. It's still, right now, the object is moving straight forward at some tangential velocity, and then the acceleration is going to cause it to turn. So this is the linear tangential velocity. So how do we find the tangential velocity? Well, remember back at the beginning of this video, I told you that the arc length is equal to the radius times the angle through which the object is displaced. And if we want to figure out, well, linear velocity is just going to be the derivative of the arc length with respect to time. So to take the derivative of the left side, we have to take the derivative of the right side. The derivative of the arc length is going to be our tangential velocity. And then the derivative of r with respect to time this is a constant with respect to time. So then the derivative of theta with respect to time is the angular velocity omega. So to find the v, and specifically, let's be very clear here, this is the v tangential. The tangential velocity is going to equal the radius times the angular velocity. So they're related by that radius, which, remember, makes sense, because if you have a very large radius, like the outside of this clock, you're going to have a higher tangential velocity than if you have a small radius like the inside of this clock. So larger radius is going to give you a larger tangential velocity for the same angular velocity. And then if I want to find angular acceleration, I'm just going to take the derivative, or a tangential acceleration, not angular acceleration. That's something else. Tangential acceleration, it's going to be, again, the derivative of the tangential velocity with respect to time. R is still a constant with respect to time. So we're going to have the tangential acceleration is going to equal the radius times the angular acceleration. That's tangential acceleration. And last but not least, remember, you may have to go back and rewatch video 1.9, but we showed that the centripetal acceleration is going to equal the tangential velocity squared divided by the radius. And that was using similar triangles and then limits as these things approached zero. But just similar triangles, we can set up that the centripetal acceleration equals v squared over r, and that's, to be clear, the tangential velocity squared over the radius. But we also know the tangential velocity equals the radius times the angular velocity, omega. So then we can simplify this down. And also we could say that it depends on what you're given in the problem, but we can say that the centripetal acceleration equals the radius times the angular velocity squared also. These two quantities should be similar in all cases. So those are a bunch of equations which we are going to practice together in our next class, solving a bunch of rotational kinematics practice problems. But for now, this is Mr. Boltri wrapping up video 5.1, and go Bears.